Hello and welcome. From this lecture, we're going to start looking at algebra with matrices. Okay, so from a young age, we might have learnt about algebra. Algebra basically means adding, multiplying, subtracting, dividing with things and coming up with complicated expressions, simplifying them, making them easy, doing products and all of these things. We'll learn how to do that with algebra beginning this week. Okay, so that's going to be the topic of this week. So let's proceed. Okay. So before we proceed to doing algebra with matrices, there always comes a fundamental question of what is a matrix, right? So we always grapple with this question of what is something in mathematics, right? So for instance, what is a number? Right? Number, quite often we think of number as representing the amount of quantity of something, but then we also do algebra with numbers. So the number itself becomes defined by what you can do with it, not just represent some quantity. Okay, so that way, a matrix, you can of course think of a matrix as purely representational, right? So it's an array of numbers, it represents some data, or it could even be an image, I mean, what is the red color of each pixel in a big image? That's a nice array. So many other data elements can be represented as arrays, so maybe it just represents something. Just like one number represents the quantity of something, a matrix represents an array of quantities of many things, right? So that could be one definite way of doing it. But we also saw, very interestingly, a matrix also represents a linear transformation. So there is a linear transformation from Rn to Rm, and this matrix can represent it. It can say how some vectors go from one space to another. So anytime you have an object which can represent a transformation of something into something, it turns out you can do algebra with it. Okay, so it seems quite fantastical, but that is not fantastical, maybe abstract, right? It seems like an abstract way of thinking about it. So that's a mathematical way of thinking about it. We'll see a little bit of that flavor, and then we'll go into concrete algebra. So once you have this representation of a transformation, you can do algebra with these objects. So because transformations, you can do compositions, and you can do one transformation after another. So based on that, things like addition and multiplication end up being defined for the underlying object which represents the transformation. So a matrix as an algebraic object is also very, very interesting quantity. So can you add two matrices? When can you add them? Can you multiply two matrices? When can you multiply them? Can you divide? Right? Division is a little strange, isn't it? So how do you think of division with a matrix and all of that? So all these kind of things are very, very interesting, and they have tremendous applications. Towards the end, we will also see all these applications, and you'll be impressed with how the algebra with matrices, the algebra and the connection to linear transformations is very, very important in all the applications that we will see. Okay, so having discussed this philosophy, let's get a little deeper into the philosophy and see how algebra and transformations go together. Okay, so here is a little bit of a segue, diversion into this philosophy of where algebraic objects come from. Since this is a mathematics course, we can live with that for a little while and then jump into the vectors and actual operations itself, right? So what is an algebraic object? An algebraic object is something, it's a quantity with which you can do all these type of operations: addition, multiplication, division, etc. So let me give you examples. We are all familiar with the integers. Integers is minus, negative numbers, minus whole numbers, positive whole numbers, 0, all of them together. We know we can do plus, minus, into quite easily. Multiply two integers, add two integers, subtract two integers. You'll always get another integer. That's easy to do. But when can I divide two integers to get another integer? Now getting another integer is very important. Of course, if you divide two integers, you will say I get a rational number, I get a real number or something like that, but that's not what I want. I want to divide two integers and get another integer, and that is only possible sometimes. It's not possible all the time, right? So only when b divides a properly, you get an integer. Okay, so this is just a little bit of philosophy on how to think about it. You can do the same with rational numbers. With rational numbers, it's very nice. You can happily divide one rational number with the other, except when b is 0. So if b is not 0, you can do that. If b is 0, you can't do division. Okay, so this is just, you see how algebraic objects behave. There are also slightly more strange algebraic objects. You have polynomials in one variable, where again you can add, multiply, divide, multiply, subtract quite easily. But division to get another polynomial happens only when some factor rule is true, right? So when b of x already is a factor of a of x, you can divide and get something. So there's division and all of that. So I'm not going to go into details here. I'm just saying how the philosophy of these operations work. So basically, algebra is like a sort of a formal abstract study of these kind of operations. So that's generally the term of algebra. You may, if you're interested, you can do a mathematics course in algebra, and you'll see higher level of abstractions of these things. You'll define things called groups and rings and all these kind of nice structures. In fact, there is a structure itself which is called an algebra, where you can do two operations together in some interesting ways and all that. Okay, so it's just a brief high-level pointer. Now from here, we want to move towards thinking about a matrix as an algebraic object. So how do you do that? For that, you need to understand the connection between algebraic operations and transformations. Okay, when you have an underlying set, that set can be transformed by a quantity, and that transformation plays a big role in the definition of the operation. Okay, so it may not be very apparent, but I'll point out how it works, and maybe you will appreciate it. It's a little bit of an abstract idea. I'll go through it a bit quickly, and then we'll see how this is used to define addition, multiplication for matrices. Okay, so it's very important. So let's start with the integers, just an example. So you have these integers here. How did we end up defining addition and multiplication for integers? Okay, so we all know addition and multiplication, but here is an interesting sort of abstract way of thinking about it, and that will help us to define addition and multiplication for matrices. Okay, so if you think of an integer a, it's just an object, but actually the integer a can be thought of as a transformation. Okay, so here is a transformation SA, which is basically, it's going to take any integer z is any integer, it will transform z to z plus a. Okay, so if you do z to z plus a for any integer, you will go back to another integer, but this is like a transformation. So this integer a defines an additive transformation under addition. It also defines a multiplicative transformation. I'm going to call it t sub a. It takes z to z into a. Right? We know how to multiply integers. So you see that an integer a, the quantity a, represents transformations. It represents an additive transformation. It also represents a multiplicative transformation. Now this is something very interesting, isn't it? At least to me, it seems very interesting, that can represent things, and you don't think of the integer usually as representing a transformation. But that's a nice way to think about it. So anytime you have an object representing a transformation, you can define addition and multiplication in a very interesting way. See, for instance, if I have another integer b, it again represents another transformation as b, and another transformation tb additively and multiplicatively. So now what about the integer a plus b? How do you think of the addition operation? Here is the trick. Basically, it represents the composition of SA and SB, right? So when you think of the integer a, it represents addition with a, integer b, addition with b. A plus b should be the composition of the two operators SA and SB. Okay. So in this particular case, all these things are trivial because I already know a plus b, there's no confusion here. So there's no need to say that a plus b represents the composition of these two transformations. Okay. Same thing with multiplication. Okay. A into b represents the composition of TA and TB. Okay. So basically, the underlying abstract idea here is the algebraic operations with integers are actually compositions of the operations that they represent. So, but the operations they represent are so trivial in this case, so it's obvious that what it should be. Okay. Now, notice what happens when you go to matrices, right? Matrices, okay, so before I go there, before we go to matrices, so when we go to matrices, this picture will become a little bit more complicated because matrices represent linear transformations, and when linear transformations are composed, you get operations with the matrices. Okay, so this is how we'll go. I'll talk about it, but before that, let's also talk about identity element and inverses. This is also a sort of a slightly abstract idea. We will also worry about what is an identity matrix. What is the inverse of a matrix? We'll worry about all this, additive inverse, multiplicative inverse and all that, because for algebra you need all that, right? So to do that, let's think about identity element and inverses for integers, right? So what is an additive identity? 0, right? Okay, so we all know about this additive identity 0. So this S0, which is Z equals Z plus 0. So you see Z goes to Z when you add 0 to it. So it becomes the identity transform. It doesn't do anything, right? It doesn't do anything. It's the same thing. Similarly, 1 is a multiplicative identity because if you multiply by 1, you get an identity transform. I as it's called, identity transform, Z to Z. Okay, so you get the identity. So 0 becomes additive identity in the integers, 1 becomes multiplicative identity in the integers. So we have to worry about what these identities are for matrices, right? So that is also something very important. Now we also know additive inverse. Additive inverse of A is S minus A, is actually minus A, right? A is minus A, we know that, that's the additive inverse in the integers. So what happens there, if you see S minus A and compose it with SA, you're going to add A first and then minus A, you get Z. So you see that S minus A composed with SA is the identity transform. So that's how you define additive inverse. So for multiplicative inverse also the same story is there. So in this particular case for integers there is no multiplicative inverse if unless A is plus or minus 1. Okay, so that's the story. Okay, so generally this inverse exists when you can when you can compose two transformations and get an identity. Okay, if you have a transformation, if you can compose it with another and get identity, then you have the inverse. Okay, so this is the abstract way of seeing how what addition represents, what multiplication represents, what is additive identity, what is multiplicative identity. We are going to take these abstract ideas and use them in matrices. So how do you think of algebraic operation with matrices? You have a matrix here which represents a transformation T. If you have another matrix B, it's going to represent another transformation S. Okay, so two matrices represent two linear transformations. So how do you think of operations such as addition, multiplication? They are defined using compositions of linear transformation. When you think of addition, you add two linear transformations, so what happens to it? Okay. When you think of multiplication, you sort of multiply or compose the transformation with itself, and then you see what happens to it, and then you define one operation. Okay. So this is the sort of idea that we use to define operations. And how do we think of multiplicative inverse? If you can compose two transformations and get the identity, then you will get inverse also. Okay. So these are the underlying ideas which we will explore, and these are the underlying ideas that we will explore in the next lecture, and at the end of that lecture you will know how to add two matrices and how to subtract two matrices, how to multiply, how to do these kind of operations very easily in a proper well defined manner. Okay, thank you very much.